Hello, everyone. Welcome. We're so glad that you're able to take time from your busy days to join us for this webinar. We're pleased to be able to offer this research update tonight. My name is Janet Heischetter, and it's my privilege to serve as the Executive Director for the DMRF. Tonight is really a special night for us. It's an opportunity for us to thank all of you for your support of the Foundation's work. Simply put, we could not do what we are able to do in the way of research, education, advocacy, and support without all of you. And we are so grateful to you, not only for your financial support, but also for the trust that you have placed in the DMRF. Thank you so much. Before we start tonight, I'd like to just make a couple of announcements about the webinar. The audio for tonight's webinar is available via telephone or through your computer speakers. If you are using your phone, your lines will be muted due to the large number of participants. If you're using your telephone, please select the phone call button in the audio pane on your attendee control panel. You will also need to enter the audio PIN that is shown in the audio pane and turn your computer volume off. If you're using the computer speakers, please be sure to select the computer audio button on the audio pane of the attendee control panel. Your questions are really an important part of this program, and we encourage you to write them down as you think of them, and we'll do our best to address them in the time that we have available for us tonight. We'll take written questions at the end of the session, and to get your question communicated to us, you need to type it into the question pane on your attendee control panel. Also want to make sure that you know that this webinar is being recorded, so people who are not able to participate in tonight's webinar will have access to it, and you also will be able to view it again if you'd like. The link for the recording will be sent to all of you as soon as it's ready, which we estimate will be sometime in mid-July. If you have any technical difficulties during the webinar, please email Jody Roosevelt. Her email is listed there on the screen, and she'll do her best to assist you with your problem. So on to our program. I'd like to just fill you in just very briefly on the DMRF and sort of our overall science and research strategy before I introduce Dr. Teller. The DMRF was founded over 40 years ago now to fill a vacuum that no other organization was poised to address, and the Foundation remains the leading dystonia patient organization today. Our goal is simply to go out of business, and the way that we are going to do this is through our research and scientific efforts. But because we know that science can never move fast enough for those who are waiting for answers, the DMRF's mission, presented here on the screen, reflects our commitment to awareness, education, and support, because we feel very strongly that no one needs to go through the dystonia journey alone. All of our work is made possible through your generous support, and again, we thank you for that. It's important to note that the DMRF funds investigators worldwide, not just here in the U.S. We believe in a global approach to achieving our goal, and we work collaboratively with others to fund the best dystonia research wherever it may be. Our science program is a multi-layered approach to advancing an understanding of this disorder. It includes grants to investigators who have an idea and come to us and present that, contracts with investigators where we go to them to ask them to do specific scientific projects, scientific meetings and workshops where we bring together experts to identify new areas for research investment. We work with pharmaceutical and the biotech industry to engage them in the dystonia cause. We're also working to support young investigators, fueling our intellectual pipeline. And finally, our clinical fellowship program, the training of physicians who will be in the community and better able to diagnose and treat dystonia today, helping patients now. The DMRF is fortunate to work with experts from around the world serving on our Medical and Scientific Advisory Council. These people are super smart, committed individuals who give of themselves very generously so that we can make the best decisions about where to invest our research dollars. And here's a photograph from our most recent MSAC meeting. The MSAC is chaired by Dr. Malin DeLong of Emory University, pictured here in the middle, who has served as our scientific director for over 20 years. His service has been a gift not only to the DMRF, but also to the dystonia community. Our Vice President of Science is Dr. Richard Lewis, pictured here on the left, who brings his strong commitment to the mission and his medical knowledge in all he does for the DMRF. Dr. Lewis works with Dr. DeLong and Dr. Teller, who's pictured on the right, and our science committee in planning for how to best move the field forward, determining the direction of our research program annually. I'd like to also take a moment to just recognize Jody Roosevelt, who's not only helping us tonight troubleshoot for this webinar, but who's also a critical member of the science and research team in her role as grants manager. Jody works to implement the funding decisions the DMRF Board of Directors makes and navigates the many administrative challenges that universities where our investigators are working present to her. So we're grateful to Jody for all of her work. Since the beginning, the DMRF has been committed to the belief that the best service we can provide the dystonia community is to work every day toward finding a cure. In 2006, the Board of Directors, true to this commitment, decided to bring on a full-time scientist to not only manage the Foundation's scientific and research program, but to monitor the entire neurological landscape to assess what advancements there may be in other disease fields that would hold promise for dystonia. We were fortunate to find and bring on board Dr. Jan Teller as our Chief Scientific Officer. Dr. Teller did his university work in Europe, where he's received his doctorate degree in biological sciences. He also holds a master's degree in animal physiology and clinical psychology. Before joining the DMRF, Dr. Teller was a very accomplished researcher doing work in Alzheimer's disease, Down syndrome, and other neurodegenerative diseases. We're pleased to have him present tonight and grateful to him for the work that he does for the dystonia community every day. It's my pleasure to now turn the program over to Dr. Teller.
Thank you for this nice introduction and presentation by Janet. I feel a little bit at a disadvantage because you saw me at least on 2 pictures and I cannot see you, so I'll be speaking through a very shiny screen, presenting you dystonia research update, something which is has become our tradition, but this is, as Janet highlighted, perhaps slightly different, more exclusive presentation for you. So obviously any research update involves research, and research is a big question mark driven by our curiosity to understand things, how they work, what causes things to happen or mishappen. But in case of dystonia, this is slightly different and flavored by the presence of suffering and disease, and in this case you see only cervical dystonia, but we really would like to find a cure for all forms of dystonia, and we are driven and inspired by patients who kind of inspire us not only by interacting with us, but also giving us some ideas what to do in research field. So obviously, I'm preaching to the choir. You know that the dystonia is not a muscular disease. It's a neurological disease which involves our brain. And we have to step back a little bit and think about the brain itself. And our understanding of the brain is really critical for our understanding of dystonia. And there are many different models of how brain works and how determines our movement in this specific case. And on your left, you see a depiction of a brain as a sort of a network of connections, which are binary, and many people believe that this is just one big computer. On your right, you see that there are real nerve fibers which really might be reflecting those connections, but perhaps they are not necessarily of a computer type. We also think that this is obviously highly abstract model of the brain, that brain structure is such that there are many small elements, small and bigger elements, and brain becomes a sort of a hyper machine, and we have to understand those, not only those elements, but also principles of it. And some people believe that maybe this is much simpler, and maybe our efforts are grossly misled. We tend to disagree. So, as I said, the brain is really the key element in this puzzle, and the brain means billions of neurons, and we are currently concentrating on specific neurons and specific connections. And we obviously know from research done primarily or initially by Malin DeLong, whom you saw on the picture just a minute ago, that basal ganglia, the structures which are deep in the brain, really are responsible for control of movement, learning of movement, and by the same token, responsible for dystonic symptoms. We know that these structures are relatively complex, although very small, and they contain at least two different competing pathways, something you probably heard about. But this is not enough just to localize the structure and in the brain and say, okay, we suspect that this is the most critical part of the brain. With all the advances of molecular biology, anatomy, neurophysiology, histology, we understood that the complexity of the striatum, the one of the part of the basal ganglia, is such that there are many different, very specific neurons, and we are just at the beginning to understand that very different neurons sit there, and they have very unique roles. Again, I won't be going into the details about this, but you see those tiny structures which are in yellow, green, or red. These are receptors, molecules, protein molecules which sit on those neurons and are perfect targets for neurotransmitters and by the same token, drugs, pharmacological treatments. So to simplify this again, to give you a sort of very general overview, we have to understand how to connect our appreciation and understanding of the brain structure and function at the very high level to the function of individual neurons, and perhaps go deeper into the neurons, or at the same time understand how neurons communicate between each other. And this is a very clumsy depiction of what the body of the neuron may look like. It's something you probably can see in school, but it also shows you that individual parts within the neuron are very critical to determine the function. And again, I have no time to go into details, but in the center of it, you see a depiction of the nucleus where all the DNA information is stored, and other structures as well. And we will be alluding to this a little bit later. So we can jump into really sophisticated science. And again, you don't have to even read the title. I'll try to explain it very quickly. This is something, since this is research update, these are very current papers which appeared within the last months. And this comes from a lab of our former MSAC member, our FUN awardee, and Grant Laxton, who actually was a grantee and is still a grantee of DMRF. This really shows a part of the nucleus where you can probably recognize and appreciate that tyrosine A is actually sitting there. And this is a very elaborate, sophisticated study showing that tyrosine A takes part in building this membrane which surrounds the nuclear envelope. And only if, once we understand the actual normal function of tyrosine A and neighboring proteins, we can start to reveal what they really do when things go wrong, like in dystonia. We can go even deeper in analysis. At least, we have people who do this. And again, our MSAC member Thomas Schwartz from MIT, and also our grantee, led a group who discovered the structure of tyrosine A. And this was done at a very high resolution. And you may say, why do we really need to know what a particular protein like tyrosine A really looks like? So it was very important and revolutionary study, which shows that for years we thought that individual tyrosines form kind of a donut, but there are 6 of them. What they showed is that this is not true, that they are interfacing also another protein called LAL1, and this protein is absolutely necessary. This was the biggest part of the discovery for tyrosine A to have actually some sort of a function. So this is one of the major breakthroughs at the molecular level, and it shows that tyrosine A finally can be targeted with chemicals, drugs, or drug candidates. This is another study, also quite new, appeared late in 2016, which comes from the group of Rose Goodchild, who is currently working in Belgium. For quite a long time, she's been associated with DMRF in many different roles. What they discovered here is that, again, something absolutely fundamental, and we are pleased that people go so deeply in this analysis, and that that they discover fundamental processes which might be responsible for dystonia. In this case, we are talking again about DYT1, so where tyrosine A is involved. And in normal circumstances, remember this nucleus on this graphic representation of the 3-dimensional representation of neuron. So exactly, tyrosine A sits somewhere in, around this nucleus. And in normal circumstances, everything is fine, and the membranes which surround the nucleus are also looking relatively fine. So it looks like that in DYT1 dystonia, there is when tyrosine A is malfunctioning, there is an altered or deficient membrane lipid distribution. So again, this is very surprising discovery, which might be opening absolutely phenomenal avenues in understanding of DYT1 dystonia and many other disorders which might be involving membranes, something which has been overlooked for quite some time. Another study which I want to highlight, again published late last year, and again the title is very technical, but I want to highlight Mendelian and sporadic disease. This is one of the first attempts by Nicole Kalakos and others, and you see the number of people collaborating to demonstrate that there might be a very common mechanism, again, basic mechanism, which would be very common to all different forms of dystonia. And this involves this esoteric signaling pathway called EIF2-alpha. This is a well-known pathway which operates also in many other diseases, including cancer. And this is the pathway, and again, don't try to study this right now. I just want to flash this in front of you to show you a certain degree of complexity. That in normal circumstances, this pathway involving EIF2-alpha sort of pivots from one state to the other and controls response of the cell to stressors, especially in the brain and in neurons. This is absolutely critical. So what they demonstrated is that if you have DYT1 compromised pathway by mutation in torsin A, or in DYT16, surprisingly, or even in sporadic dystonias, meaning where you don't have any specific gene identified, this pathway is disturbed. So this is really very novel discovery, which links this very common pathway, very well known to molecular biologists and cell biologists, to stress response and synaptic plasticity. And as we know, synaptic plasticity, and I will allude to this later, might be of critical importance in developing and maintaining dystonic symptoms. So other people perhaps cannot come up with immediate discoveries of the magnitude I showed you on those 3 or 4 slides, but they try to really understand the complexity of dystonia, and I will highlight once in a while the term complexity of dystonia. So what is surprising here is that what they did, they simply run on a computer using computer analysis all the genes which might be involved in which are involved in dystonia, not necessarily causing dystonia, but also involved in dystonia development. And they compared this to cerebral ataxia, which is a sort of a slightly different, obviously, movement disorder caused by relatively different genes. What they found that 99 of those genes overlapped. And again, if you ask clinicians, they would tend to disagree because they want to make a proper diagnosis. They want to say, no, this is ataxia, this is dystonia. But there are some commonalities which are not visible by a naked eye, which we have to pay attention to. So this really opens up new opportunities to study genetic of both disorders. And I believe the resolution won't be so great, but this is what one of the groups from Harvard compiled as all the proteins which we know as involved in dystonia, causing dystonia in this case. And we now have close to 20 of them known and several unknown. How they interact with each other. And you see that torsin A is now a big star. TAF1 is another one. SGCE involved in myoclonal dystonia and others. So this is now beginning to make sense that they are interacting with each other. So there might be a very powerful message, again, in understanding this complexity. So if you look at this and you look at the next slide, you say, what kind of complexity we are talking about? This is what researchers in cancer did, analyzing 31 different genes and proteins and mapping. This is based on real data, how they interact with each other and which are clustered in the middle, which might be of the critical importance. This is our dream that one day we will also have this kind of an image. And it's not on an image, it's really, it's a very superficial depiction of what computers can do nowadays with this information. But it's all nice at molecular and cellular level and to understand the basic mechanism, but it's a very long way from that to really understanding the brain function. And this is really a schematic depiction of real highways which operate in the brain. And it's not only basal ganglia, as you see at the upper on the upper left, but we know that cerebellum and motor cortex are involved. But somehow for many years this has been neglected, and everyone was so fascinated with basal ganglia, and rightly so, because DBS works by stimulating basal ganglia. But we now, it's almost a shame to say, we're beginning to go back to the old ideas. The cerebellum must be interacting very intimately with basal ganglia. The spinal cord might be also involved. And all those tracts which have been neglected for a number of years are now intensely studied. And this is not only studied by looking at the brain and studying anatomy, but people do real experiments. And this is one of the most beautiful experiments done in recent years on the role of cerebellum in DY2 dystonia. And you see that part of the cerebellum in this mice have been stained with so-called green fluorescent protein, which shows that researchers actually targeted a specific gene, in this case torsin A, only to this area. So, you know, in other areas this was not really affected. And what they showed is really quite surprising. It was surprising that if you mess up cerebellum by mutating torsin A specifically in this area, the mice become dystonic. And this is not entirely true if you do the same with basal ganglia. So this was very surprising, a bit contradictory, but really leading us to revision of our understanding of the brain in dystonia. This is another study published just in April of this year, which comes from Roy Silito at Baylor. And what they did a slightly different study, very complex. So again, they produced dystonic like postures in mice, but they finished this research on a very high note, because they could actually do DBS. They first messed up the cerebellum genetically to produce this dystonic symptom, but they could actually demonstrate in a beautiful way that if you do DBS stimulation of the same area, you can restore normal motor behavior of these mice. This is again a phenomenal study with tremendous consequences for translational aspects and even for clinical aspects. So we will be really cheering on and watching what these people will do with cerebellum. In the meantime, other people not really working intensely on dystonia discovered things which are of critical importance to us. And this is a study. One paper was a commentary published in a very highly reputable journal, Neuron, showing that a very specific group of cells in the striatum is responsible for stopping certain signals. So we need a lot of inhibition and actual stop signals to in order to produce smooth and controlled movements. So again, this is really pinpointing to a group of cells in the striatum which are essentially forming a basis for control of movement, whether in normal circumstances or in dystonia or other movement disorders. So when we talk about those things and the brain, I'm gradually, obviously, drifting from molecules, from atomic resolution of torsin A and cell biology and pathways into real brain and real people. And something again which has been a very touchy subject, where you see the first word of this paper, of the title, psychiatric. You know the whole story, that dystonia has been diagnosed for many years, even to this day, as a psychiatric condition, and by virtue of denial of this wrong diagnosis, people started sort of again drifting away from analyzing psychiatric features of dystonia. But this is very true, and we should not be hypocritical, and we should really study this. This again comes from Marina Tyson and her group in the Netherlands, and there is more and more papers on this subject revealing that this is not necessarily the psychiatric conditions are not necessarily a consequence of movement disorder, but they have the life of their own in the dystonia. On a kind of an almost lighter note, this is again fantastic paper published last year by David Arkadir and others on DY2 dystonia that shows which ties many things together, although it involves a very simple psychological test in which dystonia patients, DY2 dystonia patients, would take more risk than others. And this really ties together what I said about cell biology, synaptic plasticity, abnormalities in neural networks, and suddenly it shows up at the behavioral level, or you may say even affecting your daily life. So let me quickly summarize what we've been talking about so far, and this is a master slide which shows what we kind of know, what we should know when essentially clinicians, neurologists see patients. We know that we have genetic determination of many forms of dystonia. In cases where we don't have very clear genetic forms, we have genetic susceptibility. This allows people to really analyze this overlap with ataxia, for example. We know that this translates to very complex cellular behavior of different parts of the system, and involves very specific proteins, not only tyrosine A, but those hardworking receptors which really allow us to function at the brain level. This also goes a little bit at a higher level, where we have loss of inhibition and increased plasticity, where those very specific cells step in and they control go, no-go decision when it comes to movement. And finally, we have almost behavioral level, ending with psychiatric symptoms, and all that is sort of trumped by motor manifestations. And we have to remember that behind those motor manifestations, behind this movement symptoms, we have all those features which are necessary. This is very important, and this is just one example of one level. If you recall genetic susceptibility, this is what nowadays clinicians do when they diagnose people. They apply genetic testing, and this is a schematic which helps to identify which particular dystonia we are talking about. And it's a combination of finding out what kind of genes might be changed, and also with clinical features. And this translates again to a very complex way of diagnosing people. And this should be, everyone should be pleased with this, because this looks, again, slightly esoteric. It's a schematic showing how patients are actually seen in clinical environment, and what kind of different tests you have to do, from imaging, functional assessment, to goal setting, and so forth. So finally, we have a very solid way of diagnosing dystonia. But when you look at some papers, you see, and I try to point to that, unmet needs and requirements, and unmet needs. Really, there's still plenty to do, and we are part of it. And I guess I will try to fly very quickly through those slides 5 or 6 I have here. These are the newest grants which DMRF is funding. And you'll recall Nicole Kalakos, I showed you what she achieved with EIF to alpha signaling pathway, and she will be continuing with that, trying to understand the dystonia mechanism by understanding specific molecular pathways in the brain. This is really a fundamental study, and we have high hopes for good results here. Other people like Patrick Lask and Christian Schlicker from Yale University will be studying torsin A in the nucleus, because they discovered a link between so-called nuclear pores, holes in the nucleus, and torsin A. So again, it's a fundamental study, dramatically helped by our understanding of torsin A structure. Alexandra Nelson at UCSF will be studying a different form of dystonia in a mouse model of paroxysmal dystonia, which offers a lot of insight into synaptic plasticity. So although this is a very rare disorder, the synaptic plasticity, as we understand, is a universal feature of all the dystonias. Giuseppe Schiamana in Rome is continuing his investigations on striatal and pallidal connections, again in DYT1 model. He comes from Antonio Pisani's lab in Rome, and these are world-class experts in analyzing those issues using so-called brain isolated slices. Patrick Verstrecken and Rose Goodchild, and again you recall Rose Goodchild and the idea of or discovery of membrane lipids affecting torsin A and perhaps causing DYT1 symptoms. They will be continuing the study on abnormal lipid biology, doing a massive analysis of lipids in different models of DYT1 dystonia. And finally, Bill Hutchison in Toronto, the world epicenter of DBS, together with other neurologists and neurosurgeons at this center, will be doing something very brave, essentially doing intraoperative recordings. So whenever they do DBS, they will start recording and at the same time stimulating the basal ganglia to understand how this alleviates dystonic tremor and dystonia. Something very challenging which cannot be done at many places, but perhaps only a few in the world. So we are again pleased that they will be doing this. So I've been talking mostly about research and esoteric stuff, but we also have to once in a while cross the barrier, which is you name it, physical, financial, moral, intellectual, and we are going into the world of pharmaceutical discoveries and trying to find something which would cure dystonia. And the news is not very good because, as you see, the number of drugs approved by FDA goes down to the point that someone coined this phrase Eroom's law, which is kind of a reverse of Moore's law for microprocessors. And this trend is absolutely terrible. And as you see somewhere at the bottom here, the cost, the time frame is 12 to 16 years. The cost of developing a single drug now goes from $1 to $2 billion. So this makes you kind of suicidal when you see this. I don't want to really live longer because I will probably hit the bottom here. But we still are very hopeful that you can solve this problem. And people start thinking about this. Comes from Nature, very prominent weekly, scientific weekly, published almost a year ago, that you can find many different drugs which are either shelved by pharmaceutical companies or drugs which are commonly used for other symptoms but never properly tested, apart from anecdotes about the effectiveness in movement disorders and dystonia. And again, we go back to this slide I showed you at the very beginning, because these are drugs which are typically bind to receptors, very well-known receptors. And there are thousands and thousands of those drugs, drug candidates, which are available, but we simply need to thoroughly test them, either initially in animals, or in some cases where the drugs are already approved, also in humans. So our role is very strange, because we don't have billions to really support pharmaceutical industry, not that we would like to do this, but we want to be champions. And some of you may have seen this if you listen to some of my research updates before, and I keep repeating this. This is from Sir James Black, the guy who is probably has been the most successful pharmacologist of all time, and he really gave us a very good advice, which we can. Passion and conviction are needed to prevent the faint hearts from quitting. So we want to be champions in any possible way in doing that. You can also be a champion. We are not asking you to do research on EI2 alpha tomorrow, or solve the crystal structure of Torsin A, but you can join the Global Dystonia Registry, and this supported by many organizations dealing with dystonia, where you can simply volunteer in a way, providing information about yourself, and waiting for times and opportunities where we meet people with very specific conditions, with specific experiences, to participate primarily in clinical trials or clinical studies. And obviously, you can give your brain. We would like to have your brain donated to Harvard, and not now, but please consider this. Think about it. How much benefit we would get out of that. This is terrible problem. There's a tremendous shortage of brains. Brains have not been collected from dystonia patients for many years because of uncertainties in diagnosis and uncertainty in genetic testing. So I'll stop here. I believe that there will be some questions for me, and I will try to answer. Thank you.
Thank you, Jan. We appreciate that, your presentation very much. I want to just apologize to our audience. We had a technical glitch, and so you saw not only Dr. Teller's slide he was speaking about, but you also saw his next slide. So our apologies for any confusion that may have caused everyone. We have a couple of questions, so want to get to those right away. First one is, are there less invasive brain stimulation treatment methods other than like DBS that are being investigated right now?
Yes, definitely investigated, and the emphasis should be on that. DBS has become a major modality in treatment, in surgical treatment. Which does not mean that this is the only way to do it. There's tremendous progress being made, but mostly experimentally, in terms of redesigning DBS electrodes and electrical leads and so forth. But the non-invasive techniques are mostly focused on electromagnetic forces, which are generated by a variety of instruments, and this is a these are very early stages, and one has to be very cautious in applying those technologies. But there is some hope that they can, once the technical side is improved, that this can be really used on a more frequently.
And next question, what is neuroplasticity and what's its relationship to dystonia?
Right. So as the word indicates, it's plasticity. So it's the process in a very to describe it very quickly, refers to the ability of neurons to adapt to and be flexible in terms of transferring information. This is at the same time, this is not plasticity as defined as completely loose flexibility. This is not really like playing with Play-Doh. There are certain rules which govern synaptic plasticity, where connection between two neurons through synapses can be modulated. And plasticity, if you go back to your early development as a child, your brain is very flexible, can acquire different type of information very quickly. At the same time, it's not really set to perform more complex, even motor tasks, and this develops over time. So in a way, we are losing this plasticity, but losing in the good sense that we become more organized, more rigid in terms of neural plasticity. But there has to be a certain balance. That's why we emphasize that synaptic plasticity might be playing a critical role in developing dystonia very early, where plasticity does not follow a certain path to develop well-controlled movements.
Thank you. Next question. We hear a lot about the DYT1 gene. Are there other genes for dystonia that we should be aware of?
We know that there are at least 25, 26 gene associations, and we know 20 of them right now. We precisely know those genes. So the list is getting longer. All of them code for or cause very specific rare forms of dystonia. That's why I mentioned on one of the slides so-called sporadic dystonia. Sporadic means that either there's no direct genetic mutation causing dystonia, or we are still ignorant, that we cannot really find anything right now. So all those genes, and I showed a slide with those networks of different genes, all dystonia genes at one point you can say that they are very different, but gradually we understand that they might be connected through a very complex and often unknown pathways in the cell, in the neuron. So with the advent of genetic sequencing and the fact that this is becoming now commonplace in clinical environment and is becoming much, much cheaper, it would be quite easy to analyze the entire panel, all of your genes, and understand where, what's the correlation between those genes and particular symptom. And the schematic I showed you, which is useful for clinicians nowadays, is really to kind of project the genetic knowledge on the clinical situation. So not to be just blind to that, describe phenomenologically certain form of dystonia, but understand that some forms have a very profound genetic background, and if we know it, we should take full advantage of it.
Does this research that you've outlined have implications for secondary dystonia? It appears, our questioner says, it appears as though this research is mostly for primary.
Right. Definitely it has maybe not all of that research is directly relevant, but most of it is quite directly relevant. You have to understand that I started my presentation with a big question mark, and this is what we are dealing with. It's much easier to count or identify things which we know about than find out what is missing. So there is a lot of stuff that is missing in dystonia, from unknown genes to unknown protein, unknown functions, and because of that, people have to cling on to something which is more palpable and manageable in terms of research. So if there is a discovery or has been a discovery of a particular gene, be it DYT1 or DYT6 or DYT16, people immediately jump on that and say, oh, this is a certain clue. So this creates perhaps a distorted view of the field, and some people say, wait, why don't you study secondary dystonias? And the answer is that we don't know how to approach it right now. So we have to find first, get some clues from something which is more manageable in terms of research, and then we'll go from there. But whenever we deal with certain level of complexity, let's say doing a study of neural networks or circuits, this is absolutely and directly relevant to secondary dystonias as well.
Thank you. This person wants to make sure that they understood correctly one of the studies that you referred to, and asks if the study says that people with dystonia may act in a more impulsive way, if that's what the study was demonstrating. And then related to that, are there psychological differences in those with people who have dystonia?
Right. So maybe it's easier to answer the second part. Definitely, there are psychological issues, and again, this has been suppressed for many years or ignored. And I think that the current view is that in many forms of dystonia, psychological symptoms are just part of the entire symptomatology. They are not just caused by the fact that you have movement disorder and then you sort of in a secondary way you develop. Remember, your brain is affected by the disease, by controlling, by the lack of control of movement. So this sort of the effects dissipate across different neural pathways. So it's very understandable that psychological issues might be present, which does not deny the fact that there are secondary psychological issues. That someone who has a severe generalized dystonia may develop social phobias, which are not primary symptoms, but simply developed on the basis that this person is not really comfortable in social environment. And the first part, if you could remind me.
Sure. Are those people with dystonia more likely to act in an impulsive manner?
Yeah, I don't know whether I would use the word impulsive, because the risk-taking is now considered as a very sophisticated and peculiar feature of the brain, which involves assessment of situations, very often unconscious or subconscious assessment of the situation. So this study had to be done in a very clever way, not to really suggest anything in terms of risk-taking. So it might be linked to the idea of disturbed synaptic plasticity. But again, this is a very superficial statement. So again, I wouldn't necessarily associate impulsivity with risk-taking, because risk-taking also involves decision-making, so involves slightly different neural pathways in the brain as well.
Okay, thank you for that. Could you talk a little bit about what the DMRF is doing to accelerate the development of new drugs for the treatment of dystonia, and then related to that, how do people get involved in clinical trials?
Right. So as I emphasized, we can call ourselves, champions of the cause, but it's very tough to get involved. And we tried, have tried everything possible, from offering, money even to pharmaceutical companies, or sponsoring research which would direct efforts towards developing novel drugs or testing novel drugs. And I guess we've had, quite good success. I wouldn't say that in many cases this resulted in drug development, but even the most recent studies which DMRF funded resulted in redirecting some efforts. So if there was a drug candidate which everyone thought, oh, this would be it, we should do this, but no one had done anything, we took on this stuff and said, why don't we test it in animal models or in cells? And we got either positive or negative results. We also tried to interact directly with pharma in the way that we can provide this bridge towards patients, to explain to those fast-paced companies that they are dealing with real people, with real stories, with real disease, and that testing drugs is not necessarily only a process which can be done with mathematical accuracy, but something which you may have noticed on one or two slides, which is now called QOL, quality of life, that this is becoming very critical. So in this sense, we interact with NIH, FDA, and we try to build the case for that. Whether we will be successful with pharmaceutical companies would most likely depend on successful clinical trials. So your enrollment in global registry would be critical. This lowers the barrier for pharmaceutical companies, not only in terms of gathering information, but this really costs money. Without it, they would have to hire a company and approach patients. We can not only lower the cost of it, but we can provide, I believe, we, meaning not only DMRF, but all of you, we can provide much better service to the cause, because the selection of patients would be much better. Obviously, this involves a lot of money, and we can only cheer on and be champions and try to convince people to go into it, whether in the federal government or in pharmaceutical companies.
Great, thank you. One last question. Can you just speak a little bit about the DYT1 research, whether or not it has implications for other forms of dystonia?
Right. So I actually showed you a slide with this unfortunately named EIA2-alpha pathway, which in this study, they actually showed that the same effect you can generate by mimicking DYT1 in cells, or DYT6 in cells, or actually just messing up synaptic plasticity in a similar way, which is present in several different forms of dystonia. So there is some correspondence between it. Again, we are, as a field, we are just still ignorant, and we are often paying the price that we try to put different things on different shelves and different drawers and say, oh, this is DYT1 because I have DYT1, so why don't we just study DYT1? Or I have DYT6. Maybe we should just separate everything out and do DYT6. This is the biggest mistake. The answers mostly come from crossing the barriers and fusing those different fields. So Torsin A is known to interact with protein which is involved in myoclonal dystonia. So, and we still don't know, why this is happening and what would be the consequences of it. So we need more and more studies, and this stuff is very tough to do, costs money, and is very slow. And we have to admit this, that not everything ends with success. So again, just to summarize, I think that good science done in any form of dystonia leads to the sort of common good and mutual benefit among different forms. We shouldn't artificially separate this. That's why these diseases are called dystonia.
Thank you. Thank you for that, and thank you again for your presentation and your time in thoughtfully responding to the really terrific questions we received tonight. We weren't able to get to all of them, but these questions help us in determining articles for the dialogue and in determining materials that we develop. So we will address them all in some form. I just want to give you a quick note that the next issue of the Dystonia Dialogue will provide a summary of the grants approved earlier this year. Dr. Teller highlighted them, but you'll get your dialogue and you'll be able to see the written summary there. Additionally, the Foundation will be reviewing grants submitted through a special call for applications specific to musicians' dystonia, and we'll be making a decision by the end of the summer on grants to fund for musicians' dystonia. And in the fall, true to our commitment to support young investigators, we'll be issuing a request for applications for our research fellowship program to help support the scientific work of younger scientists in the field. I want to again thank all of you for your time this evening. You've been a wonderful audience. Your support of the DMRF, you are our champions. You're making all of this possible, so thank you. We appreciate you sharing part of your evening with us, and we wish you a good night. Thank you.